Hello.
Good morning, sir.
Good morning, everyone. Uh, just wait 1 minute. Allow all the students, and then we will continue our class. Okay, fine. So let's start today class. What we have discussed in the last class, I think, overview of the transformer as well as their construction of the transformer. You know, uh, I think is it clear to all of you construction of the transformer? Hello. So is it clear to all of you? No? Construction of transformer.
Yes, sir.
Okay, fine. I think all of you already covered in diploma semester also. So maybe the subject is also easier for you as a revision purpose, is not? Okay, fine. So let's today start principle of operation of transformer. Okay. Principle of operation of transformer. What is the ideal condition for the transformer? And what is the EMF induced equation? How we can drive that equation? So just try to cover today all this point. So just tell me anyone, what is the principle of transformer?
Mutual induction, sir.
Mutual induction. How we can drive that equation? Complete a statement, just tell me. Just, in a systematic manner. So today we are going to discuss the point of principle of operation of transformer. Of transformer. A condition for ideal transformer. Condition for ideal transformer. And derive EMF induced equation. EMF induced in primary and secondary winding. Primary and secondary winding. Right. So all these points today we try to discuss one by one. Okay. So let's try to first one discuss what is the principle of operation of transformer. What is happened due to the initial induction, the transformer?
So due to linkage of flux, an EMF is induced across the conductor or coil, according to Faraday law.
According to the Faraday law. Okay. Operation of transformer. So according to the this transformer, that means work on the principle of electromagnetic induction between the two coil or two circuit, we can say that. Yeah. So according to the principle of electromagnetic induction, EMF will be induced in a coil if it links a changing flux, is it not? So how we can supply given in the changing flux in the winding of the transformer. That means here we consider two winding, either LV winding or HV winding. Okay. So energy transfer between the two winding due to the mutual induction, Faraday law of electromagnetic induction. So whenever the flux, changing flux, that means changing flux leave the LV winding or HV winding, EMF will be induced. You know. So I think this is your, I think I have shown here the systematic diagram for the transformer. Okay. So this one indicated P for primary and this is your for secondary. Okay. Yes, for secondary. And number of turns of the primary and secondary coil is represented by N1 and N2. Okay. So when supply given to the primary winding, that means exciting current draw from the supply. So that exciting current produce the flux in the primary coil, and that flux, due to that changing flux, EMF will be induced in the primary coil. You know? And flux path you will find out in the core, flow through this dotted line through the core, and again this flux links the secondary coil. So EMF will be induced in primary as well as in secondary also. Okay. So here we are not supply given to any load. That means secondary side is your open. Okay. So just note down here the statement of the principle of operation. So we can say that a transformer work on the principle of a transformer work on the principle of on the principle of electromagnetic induction to magnetic induction between two coil between two coil or circuit, you can say that. Circuit. So according to the electromagnetic induction, that means according to this principle, according to this principle, EMF induced in a coil EMF induced in a coil if it links a changing flux, means phi. If it links a changing flux, changing flux. Okay. So flux is denoted here by phi. Okay. Hello. Vijay Kumar, mute yourself.
कॉलेज में मास्टर
Vinay
कितना
Vinay
क्लास क्या
Kumar.
पढ़ाता है अभी तक?
Hello. Okay. So in the previous class, we already saw that the construction or placement of the LV and HV winding near the core. Okay. So that construction, we can draw a systematic diagram here. That means primary coil and secondary coil. Okay. So whenever AC supply voltage is given to the primary coil, that means this current IE represent as the exciting current. Okay. Exciting current that is responsible for the mutual flux produced in the core and core loss component of the transformer. Okay, it clear to all of you. So first we just consider next one. Just allow him. So I think this standard notation of the parameters V1 and IE, you can write here. Just V1 is your supply voltage. So V1 equal to supply voltage. I is your exciting current, or maybe say that no load current. Since no load connected towards the primary side, secondary side. So IE is your exciting current. And phi is your present here flux, maximum flux. We say that that can be represented by F suffix M. Okay. Maximum flux. Okay. Next, what is the ideal condition for this? So this is all about the operating principle. Okay. In the later we discuss derivation of the EMF induced equation. So what is the condition for the ideal transformer. Each transformer we can say that the ideal condition for ideal transformer. Anyone?
Sir,
Sir, there is a no losses present.
No losses present.
Yes, sir.
Any other things?
the excitation current required to produce flux in the core must be 0.
Flux 0. Then how?
Sir. No, sir. No, sir. Current. Excitation current.
Excitation current. If excitation current is equal to 0, then how flux is produced in the core
No,
of?
sir. The excitation current required to produce flux
Yeah.
in the
That
core.
means
In the core.
core loss component current is equal to 0. Whatever consists in the exciting current is not. I already
Yes,
say
sir.
that exciting current consists of two components. One is your responsible for the production of mutual flux. Another is the core loss component. Okay. So if you consider that transformer is ideal, that means core loss component is equal to 0. Okay. So we can say that here we consider coil. Okay. So in coil, what are the electrical component consist actually? Resistance and inductance. Is it not? In a coil, what are the electrical component? Combination
Resistance.
of resistance and inductance. Okay. So if
Transformer.
if any coil consists of resistance and inductance. So if you consider that the core loss resistance is 0, so we can say that that means winding of the resistance we should neglect it here. Okay. And next point, we can say that whatever the flux produced in the primary coil, that must be linked into the secondary coil. That means no flux leakage take place in the transformer. Is it not? So these are few points we have considered for the ideal transformer. And last one, the core has the constant permeability. Whatever the core material you have used for the transformer core, that has constant permeability of that particular material. Okay, so that the magnetization curve for the core is that the linear in the ideal transformer. So just note all these points. That means the winding resistance should be negligible in the transformer. First one, winding resistance are negligible and next one is your no leakage flux. No leakage flux, that means whatever the EMF flux produced in the primary, that must be linked the secondary coil. Okay, leakage. No leakage flux. That means all the fluxes produced by all the flux set up by primary coil by the primary coil links the secondary coil. Okay. Links the secondary coil Next one is your the core losses is negligible. That means eddy current and hysteresis loss. Last one is your the core losses. In core losses consist of two components. One is your core hysteresis loss, and another is your eddy current loss. Is it not? Losses are negligible. Negligible. That means you may be here write down the core loss component. That means hysteresis loss and this component consists of two components, eddy current loss. Okay. Last one is your the core loss, the core has constant permeability, has constant permeability so that the magnetization curve of the core is linear. The magnetization curve of the core is linear. So these are the condition for the ideal transformer we consider first. But in actual transformer, we have to consider one by one all these components because no one exists in ideal form. That means we cannot this point may be found in the actual transformer. Okay, so when we discuss in the actual transformer, we consider all the components one by one. Okay, but first of all, we just try to assume in ideal condition and we consider this point and write the EMF induced equation in the transformer coil. Okay, the core is linear. Next, so how you can find out the EMF induced equation? We are consider all these point of the ideal transformer, and we already explained that operating principle already. So now, if you want to find out the EMF induced equation in the coil of primary or secondary, so how we can find out? Anyone just explain it? How we can find out EMF induced equation?
So first of all, according to the second law of Faraday law,
Yeah.
EMF induced is equal to minus n d phi by dt. Then we put phi equal to phi m sin omega t and differentiate it.
Okay.
And after that, the equation will be fine.
Okay. So
Continue.
this one is your EMF induced in a coil when the flux links a changing flux. That is the Faraday law of which one? Either first or second equation. Law. The statement is this statement, whatever we explain here. One student say that that means EMF will be induced. So we just find from this systematic diagram, whenever this one is your supply AC supply voltage, that means the sinusoidal nature of this voltage supply given to the transformer. So whenever the sinusoidal voltage given to the primary coil, so current, whatever the current draw from the supply, that is also sinusoidal, is not. So due to this current, MMF produced in this coil, primary coil, okay, and that MMF is responsible for the flux production, okay. So what is the MMF value? Anyone?
Sir,
What is the MMF value? Number of turns into current flowing in the coil, is not. It is equal to
and I.
MMF. Okay. So due to this MMF flux produced in the coil, and that flux links the primary coil as well as this flux find the path in this core, so that also links the secondary coil. So we will discuss the secondary part later. First, we just consider the primary coil. Okay. So since the current is sinusoidal, that means flux also follow the sinusoidal waveform, is not. So you can just write here, that means V1 is your supply voltage, AC supply voltage, that means sinusoidal waveform. This one is represent here which quantity of voltage? Capital V suffix 1, either maximum value, instantaneous value, or RMS value. V suffix 1, V suffix 1 represent which value of voltage? Hello?
Sir, AC voltage.
That is AC voltage, but in AC quantity we can represent the various component. That means either in instantaneous value, maximum value, RMS value. I think all of you are familiar with this term.
Yes, sir. Yes, sir.
So here we written here V1, that is supply voltage. So which quantity this one? RMS value, maximum value, or instantaneous value? RMS value, exactly. Any quantity if represented by capital letter in suffix, either you may be write RMS or not, but that is represent the RMS value. Okay. If we want to represent the instantaneous value of the supply, then how we can represent? Of this supply voltage, we represent here RMS value by V1. If you want to represent this voltage in instantaneous form, how we can represent?
V1 is equal to Bm sin omega t.
That means a small v is not. A small v equal to v maximum sin omega t. That is represent the instantaneous value of the voltage, is not. Hello.
Yes, sir. Yes, sir.
Okay. So just represent the value of voltage here in instantaneous form. That means small v equal to v maximum sin omega t. Okay. Small v equal to v maximum, that means v suffix m maximum sin omega t. Sin omega t. So similarly, we can represent the flux in instantaneous value also. That means phi equal to how much?
Im sin omega t.
Phi m sin omega t. phi m sin omega t So one student already mentioned that that means EMF induced equal to minus n d phi by dt. That means rate of change of the flux linkage. So just put that equation and differentiate and just tell me EMF induced in the primary coil. You want just try that one step by step. Just write the equation for the EMF induced. So according to the Faraday's second law, just write here the EMF induced in the coil equal to minus, we are discussing here which quantity? Primary quantity, you know, primary coil. First one. So what is the number of turns for the primary coil?
N1, sir.
N1. So just put here the N1 at the number of turns. Okay. N1 d phi by dt and put here the value of flux and just differentiate with respect to time. Have anyone completed this one? Put here the value of phi equal to phi m sin omega t and differentiate with respect to time. So how much it will becomes? Just put here the value of phi equal to phi maximum sin omega t. We can write here equal to minus n1 d phi by dt means what is the value of phi here? It is phi maximum sin omega t. So just put here the value of phi equal to phi maximum sin omega t and just differentiate this equation. Hello?
Yes, sir.
Let's differentiate that one.
Yes, sir. E is equal to minus n1 omega phi m cos omega t.
Minus n1 phi m cos omega t.
Omega cos omega t.
Omega cos omega t. So just write the value of cos omega t in terms of sin omega t. So
Yes, sir. Sin omega t minus pi by 2. Then minus will be detected.
then minus will be deducted. So just tell me final derivation.
Sir, E is equal to n1 phi m omega sin omega t minus pi by 2.
Okay. So if you differentiate that equation and simplify the equation, you will get almost the value of n1 omega
Phi m sin omega t minus pi by 2.
sin omega t. Okay. And right here. So just tell me the maximum value of the voltage. So you already find that We can write here just whatever you got here after the differentiation. Okay. So that means E equal to minus N1 phi maximum sin omega phi maximum omega sin omega t is not the maximum omega sin omega t, or you can just write here the direct value after the deduction of this minus sign. Okay, so just put here sin omega t. Is it clear to all of you? Okay. Or we can reduce this minus. So what is the maximum value of the voltage? Maximum. What is the maximum value of this voltage?
N1 phi m omega.
Whatever the component multiply here, that means say this one here, omega is here. Okay. So all these component is considered as the maximum value. Okay. Whatever the component multiply with the sinusoidal function, this EMF. So we can write here the EMF induced maximum value equal to how much? N1 phi m omega. Is not. So you will put here the value of phi equal to omega equal to how much? We can write here 2 phi f.
2 pi f.
And if you want to find the RMS value of this voltage, then maximum voltage divided by root 2 is not. So just simplify this equation and just tell me the RMS value. So we can just write here the. Is it clear to all of you? What is the RMS value?
Yes, sir.
That means maximum value divided by root 2 is not. So put here the value of omega equal to in terms of frequency, that means 2 phi f. Okay. And divided by root 2. So just tell me final numerical value. I think we get value of 4.44
f phi m n1.
f phi 1 phi
F phi m n1.
frequency, that means phi maximum and number of turns. Okay, n1, that means n1. So phi maximum n1 into, just right here. So this is the RMS value. Okay. RMS value of the voltage induced in the primary coil is not. So we already say that the frequency is already fixed. Suppose that we consider that 50 hertz, and this N1 is number of turns of the primary coil. So we can write also here 1 for the primary, is not. So that means EMF induced